All right, so how do you apply the concept? Well, not always. It's not always very painful. So in the case of the first example, or number 3, because it's out of order now, the derivative is very easy to come by. 3x squared minus 18x plus 27. All right, so we're going to set that derivative equal to 0. All right, so in this instance, we're only looking at cases where it's equal to 0, the derivative. I'm going to pull out a 3. Factor it. And solve. All right, so that's my critical value. All right, that's a critical value, specifically the case where the derivative is equal to 0. Fortunately, it's a function that's everywhere continuous, and also the derivative is everywhere continuous and differentiable, so we're not looking at a case where it would be undefined anyway. So we have our critical value. That could be a relative max or a relative min. So what we do is we take our second derivative. Because it's polynomial, it's also very easy to come by. 6x minus 18. And evaluate it for the critical value. So plug the critical value into my second derivative and see what kind of number you get as a result. So we get a 0. So the conclusion here, and this is the only conclusion we need at this point, is that the test fails. Too good to be true. Test fails. Need to use first derivative test. So if I needed to identify the extrema, I'd have to go back to the first derivative test, make a sign chart. In this case, it's only one critical value, so it's pretty easy. Negative infinity to 3. Stop, take a look around to 3, and 3 to infinity. And this is assuming that you have to do anything more than determine if the second derivative test is appropriate. Depending on how the question is phrased. I'll just stand up for a minute. All right, so I would just plug in some number that's less than 3 into this, not this, pointing out the wrong thing, into my first derivative. All right, if I plug in a nice convenient value less than 3, like 0, what do I get? 27, yeah, that's a positive number. All right, and then if I plug in some number bigger than 3, so ideally a convenient value bigger than 3. I don't know how much convenience you're going to get from this, but maybe you go like 10. So we'd have 300 minus 180, so that's 120, so positive, right? So positive to positive. So increasing. So our conclusion here is that there are no relative extrema. I would normally put that in here, but I get like tiny little bit of space there. So that's possible. I mean, we did a problem like this yesterday, 2 days ago. I forget when, but we did a problem like this where a cubic function, we know the breakdown of the possible breakdowns of a cubic function. It is possible that you could have an interval where it levels off, but it's not a turning point, right? So it levels off and then continues on its journey upward or downwards if it starts off high. All right, so that's a possibility. Let's take a look at number 6. Okay, so I'm taking the derivative. Continuous differentiable for all values of x. Always a good idea to have that in mind, whether you think it's explicitly required or not. Cosine x minus sine x. All right, we're finding the critical value, specifically the case where the derivative is equal to 0. So it does not, the second derivative test does not account for any case where the first derivative is undefined. Right, so that's a drawback to this approach. Also, it sort of lends itself to one of those Roman numeral type questions, multiple choice questions on a test, AP exam, where it's like, which of the following conditions are necessary in order for the second derivative test to apply? Something like that. The function needs to be continuous differentiable on the open interval, etc. So, all right, there's a bunch of different ways to solve this one. This, I think, is the best way. Just add the sine x to both sides and just consider what it is you're looking at. All right? Because whenever I see sines and cosines, I mean, I'm trained. They tried training me. They failed. I trained myself. And I trained myself to look at that anytime I see a trig function and think unit circle. All right, so I look at this and I say, where on the unit circle is the cosine value equal to the sine value? And then on top of that, I know that the x value in the unit circle is the cosine of theta, and the y value is the sine of theta. So if I'm thinking in terms of unit circle, or a particular radian measure, where would the x and y values be the same? Well, 0, if it were at 0, the coordinates are 1, 0. So the x and y values are not the same there. 45 degrees, so pi over 4. And what's the other one? They're opposites of 3 pi over 4. 5 pi over 4. All right, just be careful. We're not talking about inverse trig functions here. So we're not restricted. Because in inverse trig functions, you couldn't be in the third quadrant for either of them, arc sine or arc cosine. But these are just ordinary sine and cosine functions. They have infinite domains. All right. Now they're separated by pi units. So I know that my critical values would be pi over 4 plus pi k, where k belongs to the set of integers. Yeah, I'm getting better and better at it. So now I'm getting to the point where I'm including it because I just like writing it. It's I don't even think it's really that necessary. It's just I'm having a good time, so I'm throwing it in there.
Fair
Yeah. So then I need my second derivative. And the clock is ticking on my ability to continue speaking. You'll be out of here in like a minute. So derivative of cosine minus sine. Bless you. I would tell you the answer, but hold on. Jeez. So negative sine x minus cosine x. All right, so I want to evaluate this at my critical values. So we'll start with the pi over 4. Then I'll try, so we would figure out second derivative at pi over 4, and also maybe something in the other direction. Well, in either direction. So we'll go north of pi over 4. That would give us 5 pi over 4, as we said above. And then if we go in the other direction, we'll have negative 3 pi over 4. All right, so we're looking at, since sine and cosine of pi over 4 are both positive root 2 over 2, you could say negative radical 2 over 2 minus radical 2 over 2, which is negative radical 2. But the key here is that it has to be a negative to give a relative maximum. All right, so if I put in the 5 pi over 4, both sine and cosine are negative ordinarily, so they'll become positive root 2 over 2 in both cases, giving us just a root 2, but since it's positive, that indicates that it's going to be a relative min. All right, so it seems that at multiples, or at least turns around the unit circle from pi over 4, we're looking at relative max, and from 5 pi over 4, it's relative min. So let's see what negative 3 pi over 4 is. I don't even know. Which would be equivalent location-wise to 5 pi over 4. So at a minimum, it's going to confirm what we just suspected. And it does, because once you realize that it's the same location as 5 pi over 4, you know it's going to give you a radical 2, which is going to essentially mean the same thing. So we're looking at a final answer, or at least a statement, that we have relative min at 5 pi over 4 plus really 2 pi k, because it's full turn, and that's going to be defined when k belongs to the set of integers, and that would be the same thing for relative max, or at least the same idea, relative max and pi over 4 plus 2 pi k, where k again belongs to the set of integers. I'm really enjoying the z creation.